My name is Dr. Rob Lieb, and what we're going to do today is show you about solids, liquids, and gases. We're going to start out with the gases. Gases, as you know, are very, very, very small particles that move around randomly. And you can kind of tell this because, for example, when you're at home and you smell an onion and you're sitting in the living room, you can kind of guess or deduce that there is somebody in the kitchen cutting an onion. How do you know that? Well, the little onion juice vaporizes in the air, wafts, and gets knocked around by those little molecules and drifts into the living room. Therefore, you know that the gas molecules are moving, and you can smell them with your nose without ever having seen them or heard the onion being cut. So, what we're going to do is try to understand exactly what's taking place in the gases, in the liquids that result from those gases, and in the solids themselves. The question that we're going to answer is, how do balloons blow up? And in specifically, what I'm going to do is show you 3 different ways to blow up a balloon. Now, everybody knows how to do that. How many people have blown a balloon up? Almost everybody. And if you take a balloon, and we'll take this red one here, and blow it up, you see it gets bigger. And that's what we mean by blow up. We mean that it gets bigger. The balloon itself inflates in volume, and the question isn't, does it do that? Everybody can see that it does do that, but why does it do that? And to answer that question, what we're going to do is go back to our model. This is our model, and you can see it models what it is that we're talking about. Scientists, when they're doing demonstrations or trying to understand something, they pick something that isn't the real thing in order to get to understand how the real thing works. The thing that we're going to be using today is some BBs, a Petri dish, and we have to notice the differences between our model and what really exists. And our model is very much like the thing that really exists. If you look at a BB, you notice that all the BBs are the same, just like the gas molecules. All the gas molecules are the same. The difference between our model and reality is that the BBs are not moving. As I explained with the onion, we know that gas molecules actually do move. They move because they transport the onion scent from the kitchen to your nose. So what we have to do is modify this model in order to make sure that the gas molecules move. And how do they move? Gas molecules don't march along together. They move in a random fashion. So what has to happen is we have to move this so that it moves in a random fashion and simulates gas molecules so we can understand what's taking place. And that's what we're going to do. I'm going to move some of this stuff out of the way here. I'm going to come down here and I'm going to shake this on the table. I'm going to put the lid on top so that the BBs stay inside, and I'm going to shake it. It goes like this. And if you observe this, everybody do this, if you observe this, you will see that the BBs are moving around in somewhat of a random way. They're moving around and they are striking each other, mostly. All of them are not moving at the same speed, they're moving at different speeds. But most importantly, according to what we're going to try to explain with the balloon, most importantly, they're hitting the sides. They're hitting the sides, and when they hit the sides, they bounce off. Now, most of you have caught a baseball before. When you catch the baseball, what do you feel? If the ball comes in, you feel a pulse going back like this. Imagine if the ball came in and bounced out. How would that pulse change? Well, the thing is, if it came in and bounced out, you would feel twice as big of a pulse. So each time a BB hits the side, it imparts a force onto the side of the Petri dish. In the same fashion that when we blow into the balloon, the air molecules inside hit the inside of the balloon, bounce off, and impart a force on the rubber. That force causes the balloon to expand. So now we know why the balloon gets bigger. When we pump more gas into the balloon by adding air, the balloon gets bigger. Why? How can we change our model to simulate that action? Well, the way that we would do that is that we could take more BBs, add them to the Petri dish, and shake it, and you would see that there would be more BBs hitting the sides of the Petri dish. Just like when you blow air into the balloon, there's more air hitting the inside. When there's more air hitting the inside, the balloon expands. It gets bigger because of the larger force. All right, now you understand not only how to blow a balloon up, which you already knew, but you understand why the balloon gets bigger. Like that. All right, now I have the second question. That's the first way to blow a balloon up. Secondly, this is the balloon I want to blow. I want to blow this balloon up. I want to make this volume bigger. How can I do that? Now, I've had lots of answers from various students, and they say, well, you can drill a hole in it and add air. You can use water. No, we're going to use this balloon, and we're going to blow this balloon up with the information that we have. We're going back to our model. How does that model tell us how to blow this balloon up? Well, when scientists have a problem like this, they look at it and they try to understand what's taking place. And if you thought about it for a little while, what you'd find out is that, is there air inside this balloon? Yes. Which way is the air inside the balloon pushing the balloon? Out. Each of the gas molecules inside, when they hit the rubber on the inside, push the balloon in the outward direction. Is that all the air that's affecting the balloon? No. Air on the outside of the balloon is pushing against the outside of the balloon. And which way is that pushing? That's pushing in. So we have two gases producing two different actions on the balloon. The air on the inside pushing out, the air on the outside pushing in. What do you think would happen if I took away the air on the outside? Okay, that's what we're going to do. This is a bell jar, and what we're going to do is use this and a vacuum pump in order to test our hypothesis. Our hypothesis is, if we take the air away from the outside, the inside air will still be pushing on the inside of the balloon, therefore it should expand because the outside air is no longer pushing in. We put the balloon inside the bell jar. We attach the hose to to the vacuum pump. And remember, the vacuum pump, all it does is take away the air through the tube by means of a motor. That air reduction takes away the molecules hitting the outside. The air inside the balloon is trapped. It can't get out. So let's try and see if our experiment works. Very slowly at first, you'll see the balloon starting to expand as gas is taken away from the outside of the balloon. Eventually, we come to the point where the pump reaches its limit and the air leaking in around the seal on the bottom is about the same as the air being pumped out. When that happens, the balloon no longer expands. The rubber is also holding some of the air in. Eventually, it reaches the size it's going to get, the largest size it's going to get. Now, the next question, what do you think is going to happen if we stopped the pump and took the hose off? Stop the pump, take the hose off, and the air rushes back in. It rushes back in, it starts to pump the air inside more and more and more until the balloon is compressed back. Now, if you take this out and feel it, you'll feel that the balloon is a little bit warm. It's a little bit warm because the air on the outside, when it came back in, actually performed work on here, and that work was converted to heat. Anytime you compress air, you get heat. This is a byproduct of the experiment that we did. It raises a new question about how do things work? They work because every time something happens, more than one thing happens. And we do the experiment one more time. You never ever do an experiment just once. You always repeat it. And just to demonstrate that, we're going to perform this experiment one more time. You see, when you do the same experiment the same way, you expect the same results. If you get some different results, then you have to look back to find out what happened differently. Because the great thing about science is that every time you do an experiment under the same conditions, the exact same thing happens. But there's always more happening than you know about. That's another great thing about science. The balloon is about the same size that it was before, almost exactly the same size, because the pressure difference is exactly the same. And when we take the hose off after we stop the pump, we should see exactly the same thing happening, or nearly exactly the same thing. If we take the balloon out again, we notice that it's warm again. Actually, it's a little bit warmer than it was before, simply because this is the second time that it was done. The balloon blew up. Did we add any air? No, we didn't add any air like we did in the first time, but what we did do is change the pressure. So there are two things that are important: the number of gas molecules inside the balloon and the pressure difference inside the balloon, between the inside and the outside of the balloon. So pressure and number are very important quantities. Now let's look at our model again. What are the other things that can change the volume of a balloon? if you look at this, okay, we've already taken into account the number of BBs and the pressure because of the BBs hitting the side. What else could affect the volume of a balloon? Well, I'm sure that if you remember, if you took a balloon and you changed its temperature, that things might change. Imagine putting a balloon inside of an oven that's warm. What do you think is going to happen? All right, what do you do in order to represent that condition in our model? What we're talking about here is changing the temperature. We want to change the temperature so that the molecules act differently under the higher temperature. What do you think? Well, if you shake kind of slowly, you notice that the molecules don't move as fast. They move slowly and they hit on the side slowly. If we increase the speed, you can hear it as well as see it. They hit each other more fiercely. They hit the sides with greater velocity. And might that greater velocity cause an increase in the force imparted to the balloon? Well, before you came, what I did is I blew a balloon up and I put it into here, which has some liquid nitrogen. You can hear the balloon crackling a little bit. Let me show you liquid nitrogen, because this will lead us into our next portion about liquids. Liquid nitrogen is nitrogen from the air that is made so cold that it starts to turn into a liquid. And you can see it here. What I did is I poured the liquid nitrogen into this beaker, and you can see it's boiling like crazy. This is like putting water into a red hot skillet, because the temperature difference of the beaker at the beginning is very, very, very high compared to the liquid nitrogen. Liquid nitrogen is at about minus 200 degrees centigrade. Very, very cold. And listen. It stops boiling. Why did it stop boiling? It stopped boiling because the temperature of the bottom of the flask got to the same temperature as the liquid nitrogen. When that happens, the boiling stops. We're going to talk about boiling a little bit later, but I wanted to show you just how cold liquid nitrogen was. So what happens, do you think, when the balloon comes out of the liquid nitrogen? Let's do the experiment. Notice I put this on the warm table and it started boiling again. Here we go. As the balloon gases inside heat up, the balloon expands. The gases move faster and faster. They hit the inside of the balloon harder and harder, and it gets bigger and bigger. That crackling sound is something that we're going to look at in a little while, because balloons usually don't crackle, do they? But we're going to take a look at that as well. This is the balloon that's blown itself up. Because of pressure difference? No. Because of increased gas inside? No. Because of the change in temperature. The gas molecules are moving faster and faster, and they hit the inside of the balloon harder and harder. They make it expand. We do it one more time, and listen as I put the balloon back in the liquid nitrogen. I'm going to have to add a little bit more liquid nitrogen to the beaker. We kind of used it up. Put the balloon inside and listen. That crackling is the solid balloon. Rubber is a solid, but when it gets very cold, it changes its nature. It goes from being a ductile solid into being a brittle solid. If I did this many, many, many times, cracks would start to form in the balloon. But this is a fresh balloon, so it should be pretty good. All right, we're just about done. And we bring it back out again. It's expanding because it's warming. It's expanding almost as it did before. Rubber does not conduct heat very well, therefore I can touch it without fear of being frostbitten. And we have our balloon back again. This is what it was like when I blew it up before it got cold. So we found the third way to blow a balloon up, by increasing the temperature. And we understand why the temperature makes it increase in volume. So we have three things that cause a volume change. It's the number of gas molecules, the pressure difference, or the pressure of the gas molecules, and the temperature. Those three things control the volume. And what scientists do is they make a law up that defines how gases act. It's called the ideal gas law, and it's the pressure times the volume equals the number of gas molecules times the absolute temperature times a constant. And that constant is the universal gas constant. Okay, now, if gases get very, 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 very cold, we saw that they change into a liquid. And how do we simulate that with our model? We simulate it by pretending that the gas molecules begin to attract each other. And we can do that by just tipping the Petri dish up just a little bit so that they kind of pool at the bottom. Now, the gas molecules are still in motion. They're still moving. They still move over one another. But let's watch it very closely. Tip it up just a little bit and shake it back and forth like this. And what you'll see is the gas molecules do in fact move. But what you discover with this is that every once in a while, one of the BBs gets enough energy to break away from the others and flies off into the air. When that happens, that does happen because of an energetic gas molecule leaving the liquid behind. And that's what you smell when the juice from the onion, there are energetic pieces of that juice that fly off into the air, and those cause evaporation. So we've kind of understood a little bit about evaporation as well. And the question is, have you experienced this before? The answer is, I suspect that you have. When something evaporates very, 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 very quickly, what occurs? What occurs is boiling. That's what we call boiling. And we're going to investigate boiling right now. This is a beaker that contains cool water. I wish you could feel it, but you can't. But if I can see, I can put my hand on the bottom of it. It's not hot. And inside this beaker of cool water, I have air. The air inside this is pushing down on top of the water with the same force that the balloon, the inside of the balloon, was feeling from the air inside it, pushing out. So this gas is pushing down on the liquid, and it's keeping those energetic molecules from escaping into the air. So, what do you think would happen if I took away the gas molecules on top of this liquid? Do you think those gas molecules that are moving the liquid molecules that are moving very, very quickly inside the liquid, do you think they'd be able to escape? Let's find out. What I'm going to do is make sure this is on top very, very tightly. I'm going to take our vacuum pump again. I'm going to attach the vacuum pump to the nipple on the top, and I'm going to see if we can make this water boil just by taking the air away. Now, you'll see something else when this happens. You know that fish don't breathe water. Fish breathe the air that's in the water. And when I turn the vacuum on, we're going to discover that the first thing that happens is the air comes out of the water. Air comes out of the water, and then boiling starts. It does that very, very quickly. So watch it. Here we go. Air out, now it's boiling. That water is boiling. The fast molecules are leaving. They're being sucked up into the vacuum and taken away. If I had a thermometer in here, what you would find out, since the fast molecules are leaving, that the water is actually getting colder. I'm going to turn this off, and what should happen? The boiling should stop. It stops, and if I pull this off, you'll hear it. You heard the air go back in. Now, if I reattach it and do this experiment again, you'll notice a difference. Is there any air left inside this water? The answer is no, there isn't any. If we put a fish in this water, it would drown because there would be no oxygen for it to breathe. Watch what happens when I put the vacuum pump back on. No air coming out, just boiling. How do we get air back into the water? We have to shake it up. And this is like in an aquarium you might have at home. You have a little bubbler, and that bubbler puts air back into the water that the fish breathe. So let's simulate that bubbling by shaking this. Now the air is mixing with the water. We reattach it and see if the air comes back out again when we turn the vacuum pump on. Watch it. Air, bubbling. So the air, in fact, does come back out. That's why we have bubblers in fish tanks. Keep your fish alive. So that's the liquid state. There's lots more to learn about the liquid state, but that's all we're going to talk about today. Okay, for the solid part, what we're going to use, we have to simulate the attraction that gas molecules have for each other that becomes apparent as they get colder and colder and colder. We saw that with a liquid, they still rolled over each other, and we used the tilting of the Petri dish in order to simulate the liquid. For the solid, what we're going to do is use an evaporation dish. This is an evaporation dish that is in most chemistry labs. And And what we're going to do is put some BBs inside here, and well, let's examine the surface. You notice that the surface is curved here, so that gravity causes the BBs to want to go to the very bottom. And that simulates the weak attraction that atoms have toward each other, and this is going to simulate the coalescence of the gas molecules when they get locked into position. Now, all I'm going to do is shake this just a little bit. I'm going to shake it just a very tiny bit and watch what happens. When we shake it, you notice that all of the BBs try to get as close to each other as they possibly can. And the only way that they can get as close as they can and still obey all the laws of physics is if they form this structure. It's called a hexagonal close-packed structure. The hexagonal close-packed structure is designed to get the BBs as packed as closely as they can. They're attracting each other, and they want to get to the point where they are as close as possible. And that results in BBs that don't move over one another, and they can be simulated by this, which are magnetic BBs that really attract each other. And when they do, they form structures. And you've seen structures like this if you've ever gone down into caves. Caves have crystals that are six-sided, and those six sides result from packing of molecules on a very, very, very small basis that result in this. So, solids, liquids, gases. And we can demonstrate one thing more. If you have something that is solid, but it is flexible, and we heard it with the balloon, it actually turns into something that is brittle. This is a rubber hose, and it is solid, but it is flexible. It moves around. And what I'm going to do is show you how these things change, and it gives you a little bit more of an understanding of what solids are and all the different kinds that you have. I'm going to use the liquid nitrogen again. We'll take out the balloon here, put that over here, add a little bit more liquid nitrogen. And I'm going to place this into here. And you can hear it bubbling away. And the bubbling is taking place because the rubber hose is very hot compared to the liquid nitrogen. When it stops bubbling, what do we know? We know that the rubber that's inside the liquid is about the same temperature as the liquid itself. And if I take it out, now, you can see that the rubber, which was so flexible before, has broken into sharp pieces. These shards are the result of a transition from a plastic to a brittle phase. So we've looked at three different things. We've looked at gases and three different ways to blow a balloon up. We've understood a little bit more about how liquids work, how they roll over one another. We've seen how solids, when they get as close as they can, form crystal structures. And so now you understand a little bit more about gases, about liquids, and about solids. Thank you from the Senior Science Society.